Team 11, Knock Knock.
Hello everybody, we're Team 11, Knock Knock. We made an image processing smart door. I'm Tommy, this is Andrew, James, Aria, Matt, and Abasari. So we're just going to go through our project overview. Our customer was Professor Babakia, and he wanted us to make a smart door system that can unlock and lock a door based on recognizing the face of someone who's authorized to get into the house. So this could be a family member, it could be a friend, it could be a homeowner. And it allows our customer to secure his home without needing to carry his keys with him. And it also allows for manual locking and unlocking of the door with a key in case of an emergency. So the system consists of a camera module that is mounted outside of his door that talks to another module inside the door that actually is responsible for turning the lock.
So this is a kind of high-level overview of our system showing all of the components working together. On the far right is the user, depicted as a stick figure. Who's facing the door. The camera module is mounted outside of the door with the camera as shown. Inside the door is the unlocking module, which is responsible for actually unlocking the door. And the two communicate over Zigbee. The camera module additionally communicates with the cloud, which performs facial recognition over Wi-Fi. And we have a web app with analytics that the user can access to kind of manage profiles and manage which faces are associated with which profile, essentially.
So here's what the system looks like. The door module features a servo motor and a custom actuator, which turns our sample deadbolt lock there on the left. And the camera module has 3 holes, one for the lens of the camera, one for a power switch, which limits battery usage, and one for this red button, which operates the system. A short press prompts the system to take a picture of a user and compare it to the database, while a long press prompts it to lock the system.
So this is a picture of our web app, which essentially does all the things you'd expect it to do. You can add a user, delete users, upload faces for each user. You can also view the latest access times per user and adjust during which times of the day each individual user has access. Just below, which isn't shown, there's also a timeline showing when the recent accesses have been and by whom.
So I'm just gonna go over, I guess, the technical specs for each module. We have three main components to our project: the camera, the lock, and the cloud. The camera module is running a Dragon Board 410C development board. It's kind of like a board that houses a Qualcomm Snapdragon processor, equivalent to processors you can find in your phone. We're also using a 5 megapixel USB 3.0 camera and a Kinetis chip for communication with the lock. For the lock module or the door module, we are also using a Kinetis chip to connect to the camera module, a servo motor, and a custom 3D printed actuator. And for the cloud, we're running a server on the Amazon AWS EC2 instance running Ubuntu, and the API is written in Python using the E framework with a MongoDB backend.
So this diagram kind of just walks through what happens when someone approaches the door and uses the system. They essentially push a button, and that wakes up the camera module, which takes a picture and performs facial detection on that picture. After which it sends the cropped face that it detected to the cloud. The cloud performs facial recognition and says to the camera module whether the user is a known, A, if they're a known individual, and B, who they actually are. And if they're known, the camera module communicates with the unlocking module to actually unlock the door.
So I worked on the embedded development for our system, which consisted of programming 2 low-power ARM microcontrollers on development boards to eventually be functional with our custom PCBs. I also worked on integrating these microcontrollers with the system hardware in both the door module and camera module. And in doing this, I had to create a logical finite state machine of the user's experience with the system and how he would react to various things happening in the system. I was also responsible for sending the signals which control the servo motor that actually locks or unlocks the door. And in order to make the whole system work, I had to utilize a wireless system between the door and camera modules, which was done through these ARM microcontrollers and F antennas on our circuit boards.
I designed the custom actuator and the casing for the system. The actuator designed in CAD, printed in BU's EPIC facility. For the casings, there's standard black plastic electronics boxes, which were modified with the tools in EPIC, which seemed to be the simplest way to achieve that goal. Was also in charge of making sure the servo motor received the proper power and input signals to turn the lock on the door.
I was responsible for the design of the custom printed circuit boards, back from the schematics and actually taking the critical parts of the development boards and integrate it so they could actually interface as both a camera module PCB and a door module PCB. I also laid out these the part placements and the traces and the final assembly of the printed circuit boards. It includes the Kinetis chip, which is flashable and we can actually get code onto it, and also the F antenna design from the dev board, which currently has some impedance issues, but overall the hardware works fine.
I worked on the camera module hardware, which included designing and choosing the parts for the camera and the processing board that we would use it on. I was involved in deploying the environment on the camera board to allow for deploying our application on there, and I wrote and tested the camera application that goes through the pipeline of detecting the user's face, cropping the image around the face, sending the image to the cloud for facial recognition, and using that result to either send a lock or unlock signal to the door. And yeah, you could see a picture of the face detection and cropping in action using hard cascades in the OpenCV library. That's me. I got a haircut since then.
I was responsible for the setup and integration of the cloud environment. As mentioned, we're using EC2 instance on AWS with Ubuntu running on it, and the cloud environment basically hosts the image processing software and the web app. I was responsible for installing all the needed software dependencies and all the programs that we wrote was written for image processing to be integrated in the cloud environment and to work with the Eve REST API that we chose to use, and MongoDB for database.
So like Abasari, my work was also primarily on the cloud side. I implemented the API to the cloud using Python's E framework, which is built on top of Flask. I developed the web app using the Jinja framework, if you're familiar with that. And I implemented the facial recognition pipeline using local binary patterns histograms, which I guess several other teams have also used. I experimented also with eigenfaces and Fisher faces and found that they were very good for classifying known faces, but very bad at rejecting faces that aren't known, essentially. LBPH worked a lot better for that, and you have a crude representation of how it works there at the bottom of the slide.
All right, this is a demo of how our project works. It's a quick video. It's probably not clear of what's happening because it's all on the software side. What will happen is Tommy will press the button, and long press will cause the lock module to lock the door, and a normal press will wake up the camera module, take a picture, and then go to the cloud and do all the image processing and say yes or no. Oh.
Nice. Very good. Low latency.
So that's a normal press. I'll take a picture and do the image processing. right, our customer was very pleased with the product, and we met all the requirements.
So in conclusion, this system acts as a proof of concept that image processing could be used as a means of home security and other security in the future as image processing algorithms improve through further research. And a system like this could prevent a societal shift where you no longer need to carry keys with you or cards as a means of credentials to get into a restricted area. You can just use your face, which you can't forget. And we'd just like to thank the ECE Senior Design staff for helping us throughout this project.
How does this compare with any competing products? I know there's at least we can unlock your door through your phone. Anything else?
So we did some research on some of those projects. One that I remember is called Lockatron, which might be the one you're referencing. Our customer particularly wanted it to be a facial recognition-based system because a lot of those systems with Bluetooth they do present some security vulnerabilities.
What prevents a user from taking a picture from online and putting it up and unlocking the door?
Nothing. So future implementations of the facial recognition could use background subtraction and other methods to prevent that. For our case, the main issue we were solving was the communication, and it wasn't in our requirements to work around that particular problem. But there are methods that can get around that.
Thank you. Did you put any effort into the ability to scale, or is your product only able to work specifically one door essentially?
Specifically, our customer's door.
And then, so is there an ability to add people remotely, or how do you add somebody as a confirmed guest?
So that would be through the web app. The main user, which is our customer, would be able to add essentially profiles to the web app, which represent people who have access to his house.
So you mentioned one thing about rejecting unknown faces and one out would be more accurate than the other. Do you have any stats and figures on that accuracy? Did you do any testing?
Yeah, so we were mainly hovering around the required accuracy of 90%, both for true positive rate and true. So we kind of have multiple stages of classification here. First of all, we have to decide whether the user in question has access or not. And then after that, we have to say if they do have access, who they actually are based on our set of known users. For the former case, which is deciding whether or not a user actually has access, we were essentially around the required 90%, hovering around there, both for true positive rate and true negative rate, essentially. For the latter case, which is deciding who a known user actually is, all of the three algorithms that I mentioned, LVPH, Fisher faces, eigenfaces, they give very accurate results. I would say around 95% accuracy.
Thank you.